In this session, you're going to be introduced to Keras. Keras is the official high-level API of TensorFlow. TensorFlow is the deep learning library produced and supported by Google. It's a great library but can be quite complicated for someone who's novice. So Keras is the recommended way to access TensorFlow, and it has a focus on fast experimentation, easy and fast prototyping. It supports all popular neural network types, including convolutional neural networks and recurrent networks, but it's also very flexible. It allows you to extend its API and create your own custom types of neural networks, and can also run on both CPUs and GPUs. So the important thing behind Keras is that it is both flexible and simple at the same time. TensorFlow is quite more flexible, however it's very complicated, and for most of the common cases you really don't need to use TensorFlow. 70-80% of the problems out there can be solved through standard neural networks that are easier to build by using Keras. PyTorch and Caffe are two other famous deep neural network frameworks, and there are quite a few others out there which are not mentioned. PyTorch is very popular, especially in academia and research, but someone has to spend considerable time in order to learn how to use it properly. Keras also now supports R, so that's another one of the benefits of using Keras. And as you can see, Keras is becoming more and more popular over time. So this is a chart from 2017, but if we would graph this now, it would still be true that Keras is one of the most searched frameworks on the internet for deep learning. So Keras also gives us many options in terms of productizing models. So it's very easy to create models which can then be uploaded in a browser, in an Android or iPhone devices, or even on hardware. So when should you choose Keras? You should choose Keras if you're a practitioner and you care mainly about implementing things, getting them out fast, and running the models, getting some results. Whereas you should choose TensorFlow or PyTorch if you're doing research and you want to develop new kinds of neural networks, or when the challenge that you're facing is very complicated and you really need to come up with some custom solution for it. So Keras offers three different API styles: the sequential model, the functional API, and model subclassing. So the sequential model is very simple and is the recommended way to use Keras. So you assume that you have a single input, single output type of case, which is the most common case out there, and you can build a neural network with as few as 3, 4, 5 lines of code. The functional API lets us combine the different layers in a network in an arbitrary way. So if you want to have two networks that share some of the layers and then they get combined into one network, or if you want to have a network that performs multiple tasks in parallel, well, this is considerably more complicated than the cases the sequential API deals with. And this is where you would have to use the functional API. So these cases do not happen too often in practice. You need to have some experience with deep learning before you try and do anything like this. But if that's the case, then the functional API can cover you. So the sequential model and the functional API together, they can cover most of the cases that you can encounter. And if none of these solutions can help you out, then you can go with model subclassing. That gives you the maximum flexibility, where essentially you extend the Keras API itself. So this is what the sequential model looks like. So you just import Keras, then you import layers from Keras, and then you say, hey, I want to add 3 layers of neurons. You define the activations, and then you say, okay, fit the model, and boom, you're done. It's as easy as that. And really, this is way more than enough for the majority of cases. The functional API is a bit more complicated. This is the same example in the functional API. And what you'll notice here is that whereas previously you defined the model class and then you added layers in this model, now you have to define all the layers as objects. And you see this syntax here. This is how the layers are connected to each other. So you define an input layer, and then the input layer goes there when you define the model, and then you define these dense layers. You define a dense layer X, and then you define another dense layer X, and these are connected. Then you have to define the final output, which is also connected to the previous dense layer. So this is a bit more complicated because by using this syntax, essentially you define an object and then you make a call to another object in the same script. Using this syntax, you can combine the activations, you can merge the layers in arbitrary ways. If you want to run a sequential neural network, it doesn't make much sense why you'd want to use a functional API, because that's considerably more complicated than this, for example. Yeah, that's cleaner code, easier to understand. However, you can imagine that here, for example, you could have two other layers which are not connected with these layers, and then they get merged, for example, before the output. So the output merges all the layers together. There are some situations, there are some scenarios where we already saw some examples actually, where you might want to have 2 or 3 networks running in parallel. But however, if that's what you really want to do, then I guess you must be quite more experienced in deep learning, because you really need to know what you're doing if you're trying to connect different layers in various more complicated patterns other than the standard feed-forward pattern. And finally, we have the model subclassing API, where essentially that's not so much of an API. It's one of the ways to interact with Keras. And in model subclassing, we extend the class directly. So we take the model class of Keras and we define dense layers and the input and the output. Again, you wouldn't want to do this for a simple feed-forward model. It wouldn't make any sense. However, if you want to create layers with complicated activations which are not supported, then this is when you're going to have to use model subclassing. I don't think that you're going to encounter this kind of scenarios very often in practice. For the majority of cases, the sequential API is all that you need. So how can you use Keras? Essentially, from now on, I assume that you're using just the sequential model in Keras, and you have to do the following. You have to prepare your input and output tensors. You have to create a layer to handle the inputs, a layer to handle the outputs, and then you add stuff in between. Yeah, so that's pretty much it. So again, this is a high-level summary of this. You prepare the data, which means that you will have to do some classic machine learning stuff, like split the train of the test set, index variables, or parse the data. Then add the layers where you have to define the number of neurons and the types of neurons. Then you compile the model and you fit it into the training data. You have to choose an optimizer, in this case, the loss functions, also the callbacks, as we'll see later, which are functions which run alongside the training. And finally, you have to evaluate the model on the test data and get the various metrics. This last step actually is a pretty standard machine learning step. It's not Keras specific. So let's go with the second intro, and again, we revisit the sequential model. As I mentioned, this is the way to go for most problems. Now let's see what's happening here. We have imported from Keras the sequential model and some activations at the dense layer. So we start by defining a model equals sequential, and then we add 3 layers. The dense layers are the standard feed-forward layers with simple neurons. We use rectified linear units as the activation. Here we have to specify the input dimension on this layer because it is the first layer in our network. And then as the last activation, we choose the softmax because we have a classification problem. We can use any kind of loss function. Here we choose mean squared error. Actually, well, that's an example, but normally we have to use the categorical cross entropy for classification. And as an optimizer, we choose the ADAM optimizer with an state of momentum. And then we simply fit the model using this function here, where we can also set some parameters, such as the number of epochs, that is the number of iterations the network will train for, the validation split, where the sum of the training data will be held inside in order to create a validation set, the degree of verbosity, whether we'll get updates per epoch or less often or more often, and the batch size. That is, how many examples are fed during each training iteration. And then we can predict by simply calling the predict function. So as you can see, those fit and predict functions are pretty similar to the ones you encounter in scikit-learn. Having worked with scikit-learn and Python, you'll be no stranger to how Keras operates. So in terms of layers, the dense layer is the default layer. The standard is the default layer used in feed-forward neural networks. Keras also supports all other popular types of neurons. It supports recurrent activations, the simple recurrent neural cells, LSTM, such as the one pictured here, gated recurrent units. It also supports convolution, 1D convolution and 2D convolution. 1D convolution is used on text and audio, embedding layers for word embeddings, and also there are some other spatial layers. Dropout, it's a bit complicated because it can be added as a layer, but it can also be used as an argument in some cases. Advanced activation functions, besides the ones that are supported straight out of the box. And then some other layers like max pooling, for example, which is used in conjunction with convolution. So in terms of activations, Keras supports all the popular activation functions, the sigmoid, the tangent, the hyperbolic tangent, rectified linear unit. These are supported as arguments in the layers. More advanced activation functions, such as the Liqui-ReLU or the exponential linear unit or the parametric soft plus and all that, they need to be added as additional spatial layers. However, in practice, the rectified linear unit is going to be okay for most problems. In terms of loss functions, Keras gives us many different choices, but in practice you don't have to be confused by all those choices. What you need to remember is that we're using the binary cross entropy for binary classification and the categorical cross entropy for multi-class classification. And in terms of regression, we usually go for the mean squared error. However, we might want to go for the mean absolute error because it penalizes larger errors less. So this is domain specific. Similarly, there might be some cases where the mean absolute percentage error might be more informative, but also Keras gives us the choice of some other metrics such as the squared logarithmic error. So in general, in regression, the difference between all these errors is by how much they penalize the different scales of error that we might encounter. So, for example, in this case, you see that the black line is the absolute error. So you see that for an error of 1, the algorithm gets a penalty of 1. However, if we use a squared error, then for a penalty of 1, the model gets penalized by 1 penalty point. However, for an error of 2, it gets penalized by 4 points. Whereas absolute error penalizes 2 by 2 points. So what this means is that the squared error tries to push the network away from committing larger errors. So squared error cares more about the larger errors than about those ones. Whereas the absolute error gives exactly the same weight to all the errors. And that's why there are different kinds of errors. For example, you see that you could use the log cosh or the Huber loss, the Huber loss being another error which is useful when you suspect there might be outliers in your data, because this would indicate that maybe the squared error is going to very severely penalize the predictions around many data points. But in practice, it might not make such a huge difference. In practice, the mean squared error is the most commonly used metric. However, it's good to be aware of those different options and don't just blindly go and use a metric because everyone does this. It's good to be aware of the differences between them. If you want to read more about the subject, there are some resources which are provided in the additional content section. In terms of optimizers, again, Keras supports all the common optimization functions, such as stochastic gradient descent, which is one of the most commonly used ones, RMSProp, which is a great choice for recurrent neural networks. AdaGrad and AdaDelta are two algorithms which try to adapt the learning rate as training goes along. Adam is probably the most successful of these adaptive algorithms, as well as NADAM, which NADAM is like Adam with also a momentum component, which at least in theory, it should help Adam escape from some local minima early on in training. If you're new to this field, you can just use Adam or NADAM and get done with it because they work well most of the time. Actually, Adam is the default optimization method for Keras. In terms of regularization, we already mentioned that Keras supports regularization, and it's a very important component of neural networks since deep learning models have a tendency to overfit because of their complexity. So we have the choice of using the L1 and L2 penalty, and we can either penalize the activity, or we can penalize the weight. Keras is a bit confusing around these issues. The default option is to use the kernel regularizer. So if you read papers about regularization, and they usually assume that you're regularizing the weights, not the activity, and this is what Keras calls kernel regularizer. You can also add dropout as an additional layer, but dropout also is supported as a parameter in the dense layer. Again, we explained how dropout works. It's a very important regularization technique. And another way to regularize neural networks is by adding a noise layer. This is one of the more exotic layers in Keras. By adding noise, we can make our network more resistant to errors. Also, Keras allows the visualization of our models. So there's this function from Keras utilities called plot model. And if you run it, you can see something like this, which makes it easier to understand what's happening. And also Keras supports something called callbacks. So callbacks are functions which are called during the training, and they're called at different points during the training. So training in neural networks is structured in epochs, where during an epoch you go through the full dataset. So you might go through the dataset in one full batch, or like it's more common these days, in mini batches. So if you have, let's say, 1,000 examples, maybe you go through 10 examples at a time. Yeah, you do this because this can help you escape from local minima more easily. So callbacks can either be called after its epoch or after its batch, and can do things such as, for example, terminate when you detect not a number. This indicates that there was an error in computation causing the network to produce a not a number result. Early stopping is something else you can do. You can stop the training when you have stopped improving. And model checkpoint, this is another callback where you save the model after every epoch. Very useful if you have a very large network which is trained on a big data set and you train this thing for days. So you want to make sure that if something happens and the system goes down, the model was saved. And there's another callback to reduce the learning rate when you see that the performance of the model has stopped improving. In terms of early stopping, that's something we mentioned in the previous session. So in the early stepping approach, the idea is that you want to find the sweet spot to stop the training before the network starts overfitting. So the more you train the network, the better training accuracy you're going to get, but eventually you're going to overfit. So the way to do this through early stopping is that you keep a part of your data set, let's say 10% of your training set, as a validation set. So the validation set is not used to update the weight parameters. However, the validation set is used in order to be testing the network at every epoch and see how well it performs. So essentially, the validation set is like a proxy for the test set accuracy. So while you're training your network, if you see that the error in the validation set has suddenly stopped improving, then you stop the training. Ideally, this has helped you stop the training at the sweet spot around here. Finally, Keras also supports some data preprocessing functions. So there's a library for sequences. So for example, if you have sequences, let's say time series or language or audio or pretty much anything, these sequences need to be of the same length before they're inputted into the network. So there are functions such as pad sequences which ensure this. Yeah, so if you have two sequences, one of 2 elements and the other of 3 elements, they can both be converted to 4 elements. Another module is the preprocessing text module, where there are functions like the tokenizer that can convert text into numbers, which can then be directly inputted into an embedding layer in order to create word embeddings. Very easy to integrate into scikit-learn pipelines. There are wrapper functions available on Keras to help you implement the methods that you're using in scikit-learn, such as fit, predict, predict-probe, that's the prediction of probabilities. And you can also use things such as scikit-learn's grid search in order to search for the optimal hyperparameters of a neural network. So if you're using scikit-learn and you want to use Keras on top of it, you won't find it difficult. Finally, Keras also supports GPUs straight out of the box. So here, for example, we force, using this command, CPU processing. And with this command here, we create a GPU model and we specify we're going to run it on 8 GPUs. It's as easy as it gets. The only caveat is that you need to have NVIDIA GPUs that support the latest version of CUDA. So if you do run NVIDIA, if you have the kind of GPUs that can support CUDA, then it's very easy to use Keras for multiple processing on GPUs.